So I'll try to be quick. So I'm going to talk you about a specific tool that ISO distributes, which is called Molecfit. And it has been developed by an Austrian consortium. And the aim of the tool, actually it's a set of tools. The aim is to correct your observations for the contribution of the sky, naming the continuum of the sky, emission line, but most important, the telluric absorptions, the atmospheric transmissions. So Molecfit, okay. So this is a description of the problem. You are at the telescope, you get the light from the source, but this is not only what you get also a contribution from the sky. Even if it is night, the sky has its own brightness, so the sky gives you extra photons in terms of emission lines and a continuum. Also, the sky absorbs, the atmosphere absorbs the signal from the source. So this is what you get, an absorbed signal. It is a multiplicative effect and an additive component, which is due to the brightness of the sky itself. So this is just to illustrate. This is what you observe, object plus sky, and in the middle of the forest here, you have to recover your signal. This is just the object. This is with the contribution of the sky. Note that this is on a logarithmic scale, not linear. So the difference is high, is in logarithmic. So there are two things, two problems here. The sky contribution, which is an additive one. Usually, when you make the observations, you observe. You can observe a sky region, so you can measure the sky and then subtract from your observations, or you can approach in another way. You can create a model of your sky starting from the atmospheric conditions. You can create a model, and we provide a tool which is called SkyCalc that creates a model of the sky at that given time so that you can subtract from your observations. Or you can use another software that reconstruct the sky contribution by exploiting the sky spectra that were taken during the lifetime of the instrument. And this tool is called SkyCore. And you can find SkyCore and SkyCalc here at the software webpage of ISO. Now, I won't say any other words about the additive contribution of the sky, and I will concentrate to the second part of the problem, which is the atmospheric transmission, which is the absorptions that atmosphere do on your spectra. Just to give you an idea, this is your spectrum. These are features of the object, but you have a lot of extra absorptions here that are due to the atmosphere. Molecules in the atmosphere molecules block the light from the source, and you have to recover for this effect. This plot here, I'll show you the average atmospheric transmission. Up to, let's say, 0.7 micron, 7,000 angstrom, you have basically negligible atmospheric transmission. The atmosphere does not, the absorption. You don't have much absorption, but for higher wavelength and near infrared, you see that atmosphere absorbs a lot of light. So your object, you won't be able to see anything in this wavelength region here. So when you reduce data, especially in the near infrared, this can be a problem, and you have to correct your observations for that. Another example. Okay, there are two approaches. A standard approach, which is you observe an object, hopefully featureless, for which you know how the spectrum look like, so you can measure the transmission there. You can see how many photons you missed, so you can create your transmission curve. You can apply to your science. Or the alternative approach, which is what I'm going to describe you now, is to use a set of tools, namely Molecfit and Caltrans, that allow you to get a model of the atmospheric transmission by fitting directly your observations, and then to adapt that model to your science. So you can correct your science observation following the atmospheric model. Molecfit and Caltrans can be found here. They are standalone tools. In April, we will have this tool embedded in the CHEMOS pipeline, so you can run these tools directly in the CHEMOS pipeline to correct your CHEMOS observations. In the future, also other instruments will have these tools embedded in the pipeline. Okay, so basically there are two tools, Molecfit and Caltrans. Molecfit does a fit of your observations and it constructs an atmospheric model. Derives atmospheric, for example, derives how much water there was between you and how much water vapor there were along the line of sight. It fits how much oxygen, carbon, whatever molecule you want. It uses a radiative transfer code, so just by knowing the position of the telescope, the humidity of that night, where the telescope was pointing, all these parameters are used in the code to build up a model of the atmosphere. The tool itself accounts also for instrumental setup. The profile of the atmospheric transmission is an observed parameter, so it does not depend only on the atmosphere, but it depends only on the instrument, because the instrument has its own spectral resolution. So the signal you are going to record on the CCD is a combination of instrumental effects and atmospheric effects. So Molecfit derives both, fits both the atmospheric parameter, but also it allows you to account for the instrument setup. And you can specify which are the molecules you would like to include into your model, and also the wavelength regions you would like to use in the fit. The second tool is Caltrans. It takes the atmospheric model Molecfit has computed, it adapts it for your science case, taking into account the different air mass, for example, between the observations you have run Molecfit on and your science observation. You can run Molecfit on a standard star, for example, very high signal to noise, so you can derive a very precise atmospheric model. And then you would like to apply that model to compute the transmission correction that you have to apply to the science. Science was observed to a different air mass, so Caltrans take this into account. Also, Caltrans reconstruct the transmission considering the entire wavelength range of your science, not only the wavelength range used in the fitting, the computation of the atmospheric model. So just to wrap up, Molecfit gives you an idea of what the atmosphere looks like. Caltrans use that information and gives you as an output the atmospheric transmission, which is the multiplicative correction that you have to apply to your science to get rid of the atmospheric absorption. The entire concept and everything is written in these two papers here that I highly recommend you to read. Okay, I skip these. I might, okay. I will come back later. But just let me spend a few words on the comparison between the traditional approach, which is you observe your standard star and you retrieve the transmission from the observations. This is here, this is your standard star. You fit, more or less, you extrapolate what your continuum should look like. So you derive the transmission, the atmospheric transmission from this spline fit here. This is what you get from the observations. And this is what you get from your model, just using Molecfit. Note that you have a nice transmission curve that, because it is a model, doesn't never go beyond 1. Whereas if you have used just the observation, you get also the noise of the observations. You get uncertainties due to the fact that the points you use to evaluate the shape of your continuum might be absorbed as well. So you can have some errors here. And this is instead the model you get using Molecfit and Caltrans. It's the model you get just by fitting regions in here, where the yellow lines are. So just by, you can construct a very good model just by fitting only these small wavelength ranges. Then you can reconstruct the entire atmospheric transmission just from these small wavelength regions, because all the physical informations are encoded in here. Everything else is something that you can add, but does not improve the results too much. So now let me start a live demonstration, and I will come back to the other slides later. So to launch Molecfit, you simply have to type Molecfit GUI, and you get an empty window, of course. Then the next thing you have to do is to load the so-called configuration file. The configuration file is one of the most important elements in all the process. Tells the software, Molecfit, which file to use, which are the molecules to fit, which are the wavelength regions to consider, which are the instrumental setup parameter to look for, to fit, and everything. I will get into more details later on. Just let me explain you the basic concept first, and then the details will follow. So you go on File, and you import the configuration file, which is simply an ASCII file. So now, where do I have my examples? Molecfit examples, shooter. Just okay. So in this configuration file, there are several instructions that tells Molecfit where to look for the spectrum. So now Molecfit, having loaded that configuration file, knows what the spectrum is, the black one. Tells Molecfit the wavelength regions to fit to construct the atmospheric model. And the wavelength region, I don't know if you can see, but they are highlighted in green here. So everything that is in these green regions will be fitted by Molecfit to understand what the atmosphere look like. And it also contains some information about the instrumental setup. For example, the line spread function. Do I assume a line spread function which is Gaussian? Another profile? Do I provide one? And so forth. So, of course, you can edit the parameter file, the configuration file, to change all these parameters, but you can also edit from the GUI. So the first thing I would like to do to show you how to change is the wavelength regions on which I'm running the fit. So this is, let's say, step 1 that allows me to define the wavelength masks. So I get another window here. And I have the option to stretch the spectrum and decide what to do. I took some notes. So in my opinion, these 5 wavelength regions are not enough to fit the spectrum. So I decide on the top of my knowledge that I would like to fit also this portion of the spectrum here that contains a lot of absorption features. Ooh, smart guy. So I click here the edit mode, and I tell Molecfit to include, where is it? Oops. To include this region as well. Turn out later that this will be a very bad choice, but I don't know it yet. It's just to show you how to do things. And also, I would like to add this feature here. Okay, so I have added these two extra features in my fitting regions. Now I'm done. I save it. And now when I'm going to perform the fit, also these regions will be considered in the fit. Next step is to decide which are the molecules to include in the fit. Yep. The original file is overwritten. A backup is created. If I don't want to override the original file, I can do save as. The second step is to tell Molecfit what are the molecules to fit. So here I have a list of molecules: water, CO2, O3, everything else. I can decide to fit the molecule or simply to calculate them according to the humidity of that exposure, the humidity, the night where the exposure was taken, the altitude of the atmosphere, and a lot of other things. I simply keep the defaults for the moment. Wavelength correction. Because of the very narrow feature of some absorption line of the telluric absorptions, it's very crucial to have a very precise wavelength calibration. So sometimes the data are, the wavelength calibration of the data need to be a little bit adjusted so that the theoretical absorption features fit nicely in where the observed feature is. So I have to adjust a little bit the spectrum to have a nice match between the predicted wavelength absorption and what I measure. So, and this is a global adjustment of the wavelength range of my spectrum. This is done by fitting Chebyshev polynomials, complicated stuff, but what I can do it here is to decide to do it, and I decide the polynomial order in which I have, okay, 12 is too much, 2. Okay. So now, when I do the fitting, my spectrum will be distorted by a second order polynomial order so that the absorption features, those absorption features here, the one in the green features, falls, falls where they are predicted to be by the models. One correction. My instrument has its own line spread function, has its own spectral resolution. It affects, the spectral resolution of the instrument affects the shape of the measured absorption lines. This is something that I can provide to Molecfit. Look, dear Molecfit, this is my line spread function. So I can provide it with a so-called kernel file. Take your model, and before comparing to the observations, convolve it with my kernel, or I can decide to have Molecfit to fit a kernel, a spectral resolution that can be Gaussian, can be constant with wavelength, or it can vary with wavelength. So I decide to have a Gaussian profile that has an initial full width of maximum of 120, 2 pixels, and constant with wavelength. This is my choice. Okay, my instrument is more or less 2 pixel, has a more or less 2 pixel full width of maximum of a spectral resolution, and it is constant. Molecfit will adopt it. Okay, this is just the initial guess, so it will find what's the constant full instrumental full width of maximum of my data. Okay. Then another important parameter is the continuum. So you see here that the spectrum, has its own continuum, but the model should be set to 1. So 1 is everything is transmitted, and then you have the absorptions. So in a way, you have to fit for each chunk the continuum on the top of which you build your model. So my recommendation, and the continuum is not a global parameter, but you fit a continuum for each wavelength region. So if you have small wavelength regions, I suggest you to have a very small order to fit the continuum. For example, here, if you fit a second order polynomial for the continuum, then you can have the continuum that does this, and you totally miss the feature of the transmission curve. So in this case, the suggested thing is to have, let's say, maybe a first order polynomial, not more, so that you do not misinterpret the shape of the absorption with the shape of your polynomial, of your continuum. So, continuum, I fit the continuum and just one polynomial degree, just a slope. Yep. Yes, yes. If you increase the yes and no. For this specific wavelength region, I would have maybe have enlarged it a little bit, so that the continuum is better chosen. You can, of course, decide to fit the entire spectrum, but you will add a lot of unnecessary information. So at the end, it will take a lot of time to process, and the final result will not be that different from this configuration here. So yes, you can enlarge, but not too much, because you will not be able to, the information you are adding to the fit will simply take the process, will simply increase the computational time rather than increase the precision of your output. For this specific region, because you have the ambiguity of the shape of the absorption and the continuum, I would have enlarged it, yes. For these specific regions, yes, I would have done it. Actually, it was on my notes and I forgot to apply it, but anyway. Okay. Okay, continuum background, this is telescope background. Okay, it's not suggested for a shooter, so I don't want to fit it. Okay, now I'm set up and I start fitting. So I have to save the parameters first. Save everything, fit. Now it takes a lot of time to fit. In the meantime, I will not tell you a joke, but will enter a little bit more into details on this configuration file. As I said before, the configuration file that I have simply loaded from the GUI is an ASCII file that contains all the informations that are needed to Molecfit to do the fitting. Molecfit example, shooter original. Okay, this is the one I have used. 1 second. I don't know if it is readable. How do I zoom it? What? Minus F in what? Okay, exit from here. Okay, I'll exit. Okay, do it. Wow, I didn't know that. Thank you. I think it's not bad. And anyway, I have a backup solution, which is the following. I go back to my presentation. Okay. Ah. Here. Okay. This is the content. This is a portion of the configuration file in which you simply specify the file name to be fit, the list of molecules you would like to fit. In order to decide which are the molecules I would like to fit, you can have a look to some reference transmission spectra. If this is my wavelength range, then I know that there is water, CO2, CH4 that play a role in the computation of the atmospheric transmission. Then other parameters. Okay, I might be observing in vacuum or in air. This is a very important parameter that determines the wavelength position of the absorption features. Another okay. Other parameters are, for example, do I want to fit the continuum? 1 for yes, 0 for no, which is the which is the degree of the polynomial fitting. In this case, it was set to 3. I mean, all the parameters that I have specified through the GUI can be directly specified, have to be specified in this configuration parameter. In the distribution of Molecfit, there are a lot of examples, so you can have a large pool of example of configuration parameter you can start with, and then you can simply start from there and you modify the parameters according to the needs. Okay, I think it is almost done, still fitting. Okay, as I said at the beginning of the talk, this is a standalone version, and we are going to have very soon a release of the CHEMOS pipeline that includes Molecfit in it. So it will be embedded in the workflow. So in the workflow you will have the option to decide whether to use Molecfit and Cartrans or to use the traditional recipe of the CHEMOS pipeline to correct for the telluric feature. And we also spend a little bit of time to decide what are the best parameters you can adopt in your configuration to process CHEMOS data. At the moment, in the next release, there are no interactive features for Molecfit and Cartrans associated to the workflow, but we are working on that. So not the next one, but the other one will have also interactive features that can allow you to change quite easily and effectively the parameters of the fit. And also, you will have the option, not in this release, but in the next one, to decide whether to run Molecfit on your telluric standard and then apply the result on your science, or to run Molecfit directly on the science. The advantage of running Molecfit on the science is that you don't have any change in the air mass. You don't have any change in the atmosphere in between your science observation and the standard star observation. Of course, you can run successfully run Molecfit on the science only if you have enough signal to noise in your science data, and if you know your science spectrum well enough to avoid fitting object features instead of atmospheric features. So this is an option that the astronomer has to do. I mean, this is a decision that the astronomer has to make and can do via the CHEMOS workflow. Still running? No, it has finished. Okay, so now the fit is done, and I have a window as before, but in red I see the best fit model. So Molecfit has computed the atmosphere, has taken into account the continuum of my object and the instrumental setup so that I can reproduce the observations. Of course, the match is done only in the wavelength regions I have selected. And I can see that I have a nice match between the observations, black and red model. I can inspect other regions, blah, 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 blah. Oh, nice match. Oh, this is not a good match. This is the region that I introduced at the very beginning because I thought these absorption features were due to the atmosphere. Actually, they are not. They are simply residual skylines. So I made a bad choice here. And also I can notice that if I scroll, the goodness of my fit is becoming less good as I increase with wavelength. That means that my choice to have a fixed instrumental resolution with wavelength was not the best ever. So I would like to repeat the fit if I have enough time. Do I have, how much time do I have? Okay, I can repeat the fit. Okay, so I'm not discouraged by this first attempt. And I decide, okay, this was a bad choice. Let's remove it. I have the option to delete it. So now I'm not fitting it anymore. Then, okay, a good friend of mine told me that is a nice feature to fit. So, okay, instead of having included that one, I include this one. Oops. And I realized that having a constant spectral resolution, constant wavelength was not a very good idea. So I decided to have it variable, which means it is actually constant, no, yeah, it's variable with wavelength. Yeah. So I save it and I repeat the fit. Okay, do you have questions? Because it will take a couple of minutes. Yep. It's a real fit. Basically, what does Molecfit do? Molecfit retrieves a kind of atmospheric parameters from a worldwide database. And these parameters are a collection of pressure, temperature, and altitude. On the top of that, Molecfit, knowing these three elements, constructs a model, taking into account the presence of molecules in your atmosphere. Three parameters of these molecules are the column density. So what does Molecfit do? Will fit the column densities of these molecules. And so it creates a kind of transmission spectrum, taking into account temperature, pressure that I had got from database, and the fitted parameters that are the column density. So it is a fit. Then it convolves this model. It convolves this model with the kernel, that spectral resolution, and adjusts the continuum and the wavelength so that it compares to the data. So in that sense, is a fit. You have a process that creates a model which is based on radiative transfer code, compares to the observations, and changes the parameter so that better matches the observations.
Just to add that very soon, probably, hopefully, Molecfit will be able to read from a database that ESO, so ESO is collecting from the radiometer information of real measurements, atmospheric conditions. So these are at the moment stored, but not yet provided to Molecfit. But soon, hopefully, will be able to use it. So in principle, at any time during the night, we will be able to reproduce a real profile of the atmosphere based on real data taken on site on Paraná.
Yes, this will be a great advantage because at the moment Molecfit does not rely on the specific information you are referring to, but it relies on other data sets.
I have another question.
Yep.
Maybe I just misunderstood, but when you talk about fitting the continuum, do you mean a fit of the radiolocal continuum to the molecular line or not? Because usually when you want to fit the overall continuum, you just want to get away from the molecular absorption.
You fit everything that is inside the wavelength range. And what's inside the wavelength range is the continuum and the absorption features. So Molecfit will start from a model that has 1, and then absorption features. And this is its model. And then it has to compare it with the data that has, I don't know, this profile. So takes the model, multiplies it with a continuum, by a continuum so that it can compare it to the observations.
Sure.
So simultaneously, it fits absorption features and the continuum. So actually, you can really fit, you can really you can really operate on regions where you don't have a very well-defined continuum from the source. Because it will be a combination of source and atmospheric transmission. Everything is included into the fit. And you, by having the fit done on different wavelength ranges, you can combine the information on different wavelength ranges.
Sure, but my point is that so you don't really need to go away from the range where you are fitting the molecule.
Not really. I mean,
okay.
You can, of course, but it's not mandatory. As I said at the beginning, now I cannot. As I said, okay, I don't have the feature here. Anyway, there are, for example, before I showed that there was a curved transmission, and then you have the continuum there. Maybe I would have enlarged this wavelength region to include a little bit of continuum, almost free from telluric features. Might have helped the fit a little bit, but it's not mandatory. The advantage of Molecfit is that if you don't see the continuum of the source because of the transmission, this is included in the model.
Can you account for volcanic gases? Let's say Andes are volcanic mountains, and sometimes eruptions take place. Can you account for that?
Actually, I don't know. Well, technically, you can add all the molecules you want to the model. So if you know what are the volcanic molecules that that volcano had put into the atmosphere, you can include it into the model. Now, I don't remember on the top of my head all the molecules Molecfit has in its database, but in principle, you can add the molecules you want, if you know what the molecules are. So is it done? Yep. Okay. Now, okay, I will be very, very quick. I would like to show you that the feature that my friend suggested me to fit is nicely fitted. And even if you go far out with the wavelength range, the fit is still good. Red is fit, black is observation. Okay, now I have run Molecfit. I have elaborated a model for my atmosphere that takes into account the column densities of all several molecules and the instrumental setup, such as instrumental line spread function, instrumental spectral resolution. Of course, I would like to create a global atmospheric transmission to be able to apply it to my data. So I've done the fit, now I apply the telluric correction to my science. In this case, my science is also my spectrum, so I will correct this spectrum. Apply the correction. Now I'm rerunning it. I'm extrapolating the information that I have collected only using these small wavelength regions. I'm extrapolating it to the entire spectrum. And you will see that even if I was not including these features here, you will see that my model contains enough information to correct for these features as well, and to correct also for these features. Why is that? Because the molecules that are responsible for these features are strictly correlated with the molecules that are responsible for these features here. So the trick is not to fit the entire spectrum, it will take forever, not to fit regions where you have no signal, you will be dominated by noise. Just select small chunks where you have, for example, a well-defined feature. You can really rely on the information, it's in there. Here you have enough signal, you have strong features. Here you have a very strong absorption features. You can rely on those small and well-selected ones. These are enough to get all the information on all the wavelength range to compute the atmospheric transmission. Still take a little bit of time. The standalone tool does not have the lazy mode to take advantage of. So every time you run it, it actually executing it. So it takes time. Come on. It was faster when I proved at home. When I tested at home, it was faster. Pardon? Okay. Now it's done. And here you have a plot that shows the observation in black, the model in red that I showed you before, and in green, the corrected spectrum. So you see that the regions here that have basically no signal were nicely corrected. Okay, you still have some spikes, but that's the noise. Cannot do anything about it. And the regions here are nicely absorbed. Okay, maybe I still have a little kink here. If I would have time, I would have include a small bit here to include it in the model, but okay, this is what I was able to obtain. And you see here that the features that I thought at the very beginning were associated to atmospheric transmissions remain there because they're not due to the atmosphere at all. They're simply into the data. So green and black here coincides as is supposed to be because those features here are in the data, and they're not due to the atmosphere. Okay, now the fit is done. And what I can do now is I can inspect if I remember where it has saved it. Yeah, it should. Okay, where is it? Transmission. Molecfit creates a lot of outputs. The most important one I would like to show you is this one, which is basically your atmospheric transmission. This is the correcting function you have to divide your data for in order to get rid of the absorption from the atmosphere. That's it.
Are there any more questions? Are there questions online? If not, I would like to give the microphone to Henry, who wants to go through a few points for the preparation of the hands-on tutorial.